Have you ever thought about uh, the math behind like the cosmos? I mean, like using tools that are like over 1,500 years old. It's kind of crazy, right?
Yeah.
To think that like people so long ago could like predict the movement of stars,
Yeah.
and they did it all with like ancient syllables and stuff. Today we're going to be diving into all that. We're talking about a real like mathematical engine, but not one made of like gears or anything like that. This one's made of pure like brain power. It's pretty awesome.
Yeah, it's really fascinating to think about.
Yeah. So we're going deep into these three verses 10, 11, and 12 from this guy, Aryabhata.
Oh yeah, Aryabhata.
Right. Have you heard of him?
Yeah, absolutely. A
Oh,
giant in the world of like early mathematics and astronomy.
totally. Like back in the 5th century CE during the Gupta Empire in India.
And the Gupta Empire, I mean, that was a real golden age, right? For like science and culture and everything.
Oh, yeah, for sure. And Aryabhata was right in the thick of it, working in this place called Kusumapura. It was like a major center for learning and stuff.
A real hub, like you said, of intellectual energy and advancement.
Yeah, exactly.
Yeah.
So these three verses we're looking at, they're like interconnected pieces of this math engine. Each one's like super important for predicting how the stars and planets move.
I like that analogy.
Thanks. So verse 10, that's like the foundation, right? It's all about this thing called a sine table.
Right. It's like the basis for so much of trigonometry, especially back then.
And then verse 11, that's where things get really trippy. It connects time and the Earth's rotation. Like, how are those even related?
Yeah, it's a really crucial link.
Yeah, it is. And finally, verse 12, that's the math behind it all, the rule that makes the whole system work.
Right. The underlying principle, the logic that drives the entire model.
Totally. Now, to understand all of this, we have to kind of step back in time a little bit. Back then, they thought the Earth was at the center of the universe, with all the stars stuck on this giant spinning sphere.
Celestial sphere, right?
Exactly, that's what they called it. And so Aryabhata, he needed some serious tools to figure out how all those stars and planets moved against this spinning backdrop.
He needed ways to measure angles and distances and how those things changed over time.
That's exactly what these verses do. So for this deep dive, we're going to be looking at the actual text of these verses straight from Aryabhata's own work.
Awesome.
Yeah, it's going to be a wild ride. Let's jump right in. First up, verse 10, the sine table foundation.
Okay, verse 10, lots of information packed into a pretty short statement.
Yeah, it's pretty dense. So here's what it says in Sanskrit. Maki vaki faki thaki daki naki naki hashaskaki kika shaki kaki kovaklaki taki kahiota facha kalatajo. I know, it's a mouthful.
That's Sanskrit for you.
But like hidden within all those crazy sounds is a ton of math. It's pretty cool, actually.
It is. And that last bit there, that phrase, kalara de che, that's our first clue.
Right. What does that even mean?
It means like parts of our signs in minutes of arc. A little confusing maybe, but we'll break it down.
So, Jad, that word actually comes from the word for a bowstring, like on a bow and arrow.
Yeah. And if you think about a bowstring, it's like the half chord of a circle.
Oh, yeah, I see it.
So basically, the sine of an angle is related to the length of this half chord inside a circle.
And that's where the R comes in.
Exactly. R stands for radius, the size of the circle. Aryabhata was using something called the R sign, which is just the sine multiplied by the radius.
So it's like scaling the sine value up.
Exactly. Then arda just means parts or increments, like the individual pieces of the sine table. And kala, that means minutes of arc, the tiny angles we use to measure stuff in the sky.
Okay, so that explains the kala ardija part. But what about that whole first part of the verse, all those weird syllables?
That's the really cool part. Those syllables actually encode numbers.
What, like a secret code?
Totally. It's called Aryabhata's verse 2 code. He basically invented his own shorthand for writing numbers.
Whoa, so each syllable represents a different number.
Yep. So maki, that first one, that's 225. Baki is 224. Paki is 219. And it keeps going like that for all 24 syllables.
24 syllables, 24 numbers, that's crazy. But those numbers, they're not the actual R sign values.
Got it. They're the differences between the R sign values. Like imagine you're climbing a staircase.
Okay, I'm climbing.
These numbers, they're not telling you how high you are at each step. They're telling you how tall each step is.
Oh, I see. So if you know how tall each step is, you can figure out the total height you've climbed.
That's exactly it. So the first step, 225, that's the R sign value for the first angle. We're dividing 90 degrees into 24 equal parts. So that first angle is 3 degrees and 45 minutes.
Oh, okay. I'm following so far.
So getting the next number, 224, that's not the R sign for 7 degrees and 30 minutes. It's how much the R sign increases from 3 degrees 45 minutes to 7 degrees 30 minutes.
Got it. So to get the actual R sine value at 7 degrees and 30 minutes, I got to add those two numbers together. 225 plus 224.
That's exactly it. And then you add the next difference, 219, to get the R sine for 11 degrees 15 minutes, and so on, all the way up to 90 degrees.
Wow. It's like a puzzle, isn't it?
Totally. And if you add up all 24 of those differences, you end up with 3,438.
3,438. What's so special about that number?
That's Aryabhata's value for R, the radius of the circle he's using for his calculations.
Okay, so at 90 degrees, the sine is 1, right? Because it's like the opposite side over the hypotenuse, and in this case, they're both the same length.
Yep, so the R sine at 90 degrees is just the radius R, which means R is 3,438.
But how did he come up with that specific number for R? Like, that seems super precise, especially for back then.
Well, he knew a lot about circles. Like, he knew that a circle has 360 degrees, which is 21,600 minutes of arc. And he also knew that the circumference of the circle is 2 pi, where R is the radius.
2 pi, that sounds familiar.
Yeah, it's a pretty important formula. And if you rearrange that formula to solve for R, you get R equals the circumference divided by 2 pi.
So you just plug in the numbers, right? 21,600 divided by 2. What does that give you?
Gives you about 3,437.7, which Aryabhata rounded up to 3,438 to make things a little easier.
Smart. So he was working with whole numbers, which makes sense, but still, that's insanely accurate to get that close without calculators or anything.
It really shows how deep his understanding of geometry was and how much he knew about the cosmos.
Yeah, it's mind-blowing. So just to give some examples, at 3 degrees 45 minutes, the R sine is 225. At 7 degrees 30 minutes, it's 449. At 11 degrees 15 minutes, it's 668, and so on, all the way up to 86 degrees 15 minutes, where it's 3,431. And then finally, at 90 degrees, it's 3,438.
Exactly. And if you compare those R sine values to modern sine calculations using that same radius of 3,438, they're almost identical. Like for 3 degrees 45 minutes, the modern sine times 3,438 is about 224.86.
That's like basically the same.
Right. It's incredible how accurate he was with the tools he had back then.
It's unbelievable. And the craziest part is this is just one verse. This whole verse, verse 10, is basically the world's first formal sine table.
It's pretty remarkable. Centuries before anything similar was developed anywhere else.
And it wasn't just some theoretical thing either. This sine table was like a really important tool for astronomers back then, during the Gupta Empire.
Oh, absolutely. It was essential for calculating planetary positions, predicting eclipses, even determining the lengths of shadows cast by sundials for telling time.
So it had practical applications as well.
Very much so.
Right.
And its influence, I mean, it's spread far and wide, not just within India, but eventually to the Islamic world and beyond. It really laid the groundwork for trigonometry as we know it today.
It really is like the seed of a whole branch of math. Crazy to think about, right?
Yeah, it's mind-boggling.
All right, so that was verse 10, the sine table foundation. Now let's move on to verse 11, which is all about time and the Earth's rotation.
Okay, verse 11, this is where we start to see those connections you mentioned earlier between abstract math and the physical world.
Yeah, it's pretty cool. So here's the Sanskrit. Pratnaiti galaba hayugasha gra javo bavasharka samalipta vagrahan navakhirao pachaka shipsamitya.
Another mouthful. But like the very first part of this verse is just amazing.
What part?
It says, the star sphere moves 1 minute of arc in one breath. Like, how cool is that?
1 minute of arc in one breath? That's pretty poetic.
Right. It's like connecting the human scale to the cosmic scale.
Yeah, exactly. So let's break it down. But that's the celestial sphere, right?
Right, the giant sphere with all the stars stuck to it. The one that seems to rotate around the Earth.
I mean, we know now that it's actually the Earth that's rotating.
Of course.
Yeah.
But in Aryabhata's model, it was the celestial sphere that was moving.
Okay, makes sense. And kalad, that's a minute of arc, right? Like a tiny angle in the sky.
Exactly. And prit, that's where it gets interesting. That means breath. Like a single inhale and exhale.
Whoa, hold on. So he's saying that the entire sky shifts by 1 minute of arc every time we breathe.
That's what he's saying.
Mm-hmm.
And he actually calculated how long a breath is.
How did he do that?
Well, in the Indian system of timekeeping, a day is divided into 60 gadas, and each gada is divided into 60 gigas, and each vidyuts is divided into 6 pruts.
Wow, they really broke it down.
They did. So that's 60 times 6, which is 21,600 pruts in a day. And since a day is 86,400 seconds, that means 1 prut is about 4 seconds long.
4 seconds. That's about how long it takes to breathe in and out. That's crazy.
Yeah, it's a pretty amazing connection. So he's saying that every 4 seconds, the whole sky moves by a tiny bit.
And from that, he could figure out how long it takes for the celestial sphere to rotate completely.
Exactly. There are 21,600 minutes of arc in a full circle, right?
Yeah.
360 degrees times 60 minutes per degree. And if each minute of arc takes 4 seconds, that means a full rotation takes 21,600 times 4 seconds.
Which is 86,400 seconds or 24 hours. That's exactly how long a day is.
Yep. That's what we call a sidereal day, the time it takes for the Earth, or in Aryabhata's case, the celestial sphere, to make one full rotation relative to the stars.
Pretty impressive, right? But I heard that some parts of verse 11 are a bit harder to figure out. Like, what about those phrases, Kayugashe grahajavo and samalipta fagratani navaparalapashikisha sametya?
Yeah, those are definitely more complicated, and there's still some debate about what they mean exactly. Kaigashe Grajava might be about the speed of planets as they move through the zodiac, or it could be related to yugas, those huge cycles of time in Indian cosmology. And Samalipta prāṇa seems to involve some numerical constants, maybe the number 9, and it might be connected to calculations of like revolutions or angles, maybe for predicting eclipses.
So those parts are still kind of a mystery.
Well, we're still working on it.
Huh.
But the main point, the breadth-to-arc connection, that's super clear and incredibly important. It connects the angles from verse 10 to the passage of time.
Yeah, it's like the glue that holds the whole system together.
Exactly. And it allows us to track the movements of planets and other celestial objects, especially within the framework of Aryabhata's chosen epoch for the Kali Yuga, a crucial concept in Indian astronomical calculations.
So even though those other parts are tricky, the main idea of verse 11 is still pretty clear.
Definitely. It's all about connecting time and motion in the cosmos.
Awesome. Okay, so we've got the sine table foundation from verse 10 and the time motion link from verse 11. Now let's tackle verse 12, the math behind it all.
This is where we get into the nitty-gritty of how that sine table is structured, the logic that governs those differences we talked about earlier.
Okay, so verse 12, here it is in Sanskrit. Pratama kapajara yaruna kanteta bityaram tat pratma yarda yarasaistais tarunanishen.
Another beautiful Sanskrit verse. But what it's basically saying is that those differences in the sine table, they decrease in a very specific way. It's not just a simple subtraction each time.
Oh, right, because the sine function is curved, so the differences should get smaller and smaller as you get closer to 90 degrees.
Exactly, you're getting it. So, verse 12 describes this recursive rule, where each new difference is equal to the previous difference minus a correction factor.
A correction factor, okay. So how do we calculate that?
It's based on the cumulative r sine value up to that point, divided by the very first r sine difference, which was 225.
So like the first difference is our benchmark.
Yeah, exactly. Let's walk through it with an example. The first difference is 225. That's the r sine for 3 degrees 45 minutes. The second difference is 224. So to get the correction factor, we add those two together, 225 plus 224, which is 449. Then we divide that by 225, the first difference.
Okay, so 449 divided by 225, that's about 2.
Right. So the correction factor is 2. And we subtract that from the previous difference, 224, to get 222.
222, that's pretty close to the actual third difference in the table, which is 219.
Exactly. It's not perfect, probably because of rounding, but it shows the general principle.
Hmm.
That we can do the same thing for the next step.
Okay, let's try it. So the actual third difference is 219. We add that to the previous cumulative value, 449, to get 668. Then we divide that by 225, which is about 3.
Right. So 3 is our new correction factor. We subtract that from the previous difference, 219, to get 216.
216. And the actual fourth difference is 215. Again, super close.
You got it. So even though there are some slight discrepancies, it's clear that this rule captures the basic idea of how those differences decrease.
Yeah, it shows that Aryabhata was thinking about how the rate of change of the sine function behaves.
Exactly. And that's pretty advanced for his time. Some scholars even think this is like an early form of calculus.
Wow! Proto-calculus in the 5th century. That's incredible.
He wasn't just giving a list of numbers, he was explaining the logic behind them.
Right. So verse 10 gives us those key r sine values, and verse 12 tells us how to understand the pattern, how those values change.
And together, they create this powerful trigonometric system, allowing you to calculate sines for all sorts of angles.
And as we talked about earlier, those sine values were essential for all sorts of astronomical calculations.
Absolutely. So let's take a step back and look at the bigger picture. We've got verse 10, the data, verse 11, the time-motion connection, and verse 12, the mathematical rule.
Three verses working together like a well-oiled machine.
A cosmic engine, as you put it earlier. And this engine was capable of some pretty amazing predictions. Eclipses, planetary movements, the timing of seasons, all sorts of
It
things.
was a real breakthrough. It changed how people understood the cosmos.
It did. And for the Gupta civilization, this had huge practical and cultural implications. They could plan their agriculture better, time their religious ceremonies more accurately, and get a deeper understanding of the cyclical nature of the universe.
It must have been a really exciting time to be an astronomer.
I bet it was.
Hmm.
And the accuracy of Aryabhata's calculations is still really impressive. Like, that R value, 3,438, and the breadth to arc connection, they're still pretty close to what we know today.
Yeah. I remember seeing that some AI analysis found that his sine values were something like 98% accurate compared to modern values.
It's amazing. For the 5th century, that's just incredible.
Yeah. But it wasn't just about getting the right numbers, it was about understanding the universe, right?
Absolutely. There must have been this sense of awe and wonder, this desire to unlock the secrets of the cosmos.
It makes you think, doesn't it? Like, how did he even come up with this stuff?
Yeah, it's pretty mind-blowing. And his work didn't just stay in India. It influenced later scholars like Bhaskara and the Kerala school.
And it eventually made its way to the Islamic world too, right?
Yeah, and played a big role in the development of trigonometry as we know it today. So, in a way, these verses are part of the global history of math.
So it's not just ancient Indian math, it's part of everyone's mathematical heritage.
Exactly. It's a shared legacy.
So, to sum it all up, we started with verse 10 and those crazy encoded sign differences. Then verse 11 blew our minds with that breadth to arc connection. And finally, verse 12 revealed the elegant mathematical rule that makes the whole system work.
3 verses, one amazing mathematical engine.
Aryabhata really changed the game. He took something as mysterious as the movements of the stars and planets and turned it into a system that could be understood and predicted.
And he did it all without the tools we have today. No calculators, no computers, nothing. It's a real testament to human ingenuity.
Absolutely. So next time we do one of these deep dives, we should definitely explore how Aryabhata used this foundation to tackle specific astronomical challenges like predicting eclipses and charting the courses of planets, because he does all of that in the later chapters of his work.
Yeah, that'd be really interesting. Seeing how he applied these tools to real-world problems.
Totally. So think about it, everyone. The math we use today to understand the universe has roots stretching back over 1,500 years to minds like Aryabhata's, who were building their own cosmic engines with nothing but their brains and the stars to guide them. It's a pretty amazing story.
It really is.
And it makes you wonder, what other secrets are hidden out there waiting to be discovered? What other cosmic engines might we build in the future?
That's a great question, and one that we'll keep exploring in future deep dives.
That's right. So keep thinking, keep wondering, and keep exploring. And we'll catch you next time on The Deep Dive.